All right, so I don't have any comments on the exam, middle of grading it. I hope you get it to you Wednesday. Can't promise. Certainly by Friday, but I hope you get it to you by Wednesday. Any questions? Okay, let's start. So you probably remember, I hope you remember, a week ago Wednesday, we discussed the fact that Broglie had said we discussed the fact that because of the way Einstein had pointed out that photons come in packets, de Broglie had suggested that all matter, and then those packets then have a wavelength, and the wavelength is associated with the momentum. And de Broglie said, whenever you have matter, there's somehow a wavelength associated with it. And then there's a momentum associated with it. And we said kind of the view of this is if I have, remember the slow wave and some people in a boat, they sort of see this as a wave. But if I have a very intense short wave, well, by intense, I really just mean short wavelength wave. And this thing hits these people, it's going to feel more like a wallop. It's going to feel like something that packed momentum. And so with this being a wavelength, lambda, or that being a wavelength, lambda, the thing that has a smaller wavelength in the denominator has a bigger momentum. Okay, and that's as far as we went towards getting towards quantum mechanics. Then we stopped and did the exam. So let's come back, though. As I mentioned, in fact, so light behaves like matter and a wave. And I told you that electrons, in fact, behave both like a particle and a wave. Electrons, if you send them at a screen that has a slit, and you know about interference, they'll interfere with each other. You'll get an interference pattern. That's really bizarre. How can I fire electrons? Before I showed a diffraction pattern, but let me show the double slit experiment. I assume you're familiar. Anyone not familiar with this? You've seen this, right? And you get this pattern of this interference pattern with light. But if you do the experiment with electrons, you get that. And again, as I mentioned, when the electrons come in, it's not that one electron makes that pattern. It's that on average, the electrons make this pattern. They don't uniformly light up the screen. They're more likely to fall here and less likely to fall here. Okay? So that leads us then to a fundamental idea from quantum mechanics. A fundamental idea. The notion is that there's something about the electrons, or any matter in fact, which is a wave. But what's a wave is subtle. It's not that somehow the electron is, well, it's not that it's somehow a wave. It's that it has certain properties that act like it was a wave. And in particular, it has something called a wave function, psi, which we're going to spend most of the class talking about today. In fact, we're going to spend the next 3 weeks talking about. It's a mathematical thing. And the goal in quantum mechanics is to find what this wave function is. And it's a function, just, function. Cosine is a function, sine is a function, x squared is a function. This is a function of x and t. It's a wave function. And having found it, which we're going to talk about, what I then observe is I say, psi of x of t is somehow, it's telling me the probability of something. So here when I had this double slit, electrons hitting it, and I said that, well, they kind of make this pattern, which when a lot fill in, it looks like that. This is going to describe the probability. In other words, this curve I would draw, and I could calculate it for light, classical interference pattern, I would say that is the probability. Well, in this case, that's just x, and I don't really have time in this problem. So the probability of the electrons landing at a location x would be p of x. And it's going to turn out what that is. That's essentially the square of the wave function. Okay? So we're going to find the wave function, this mathematical thing, and then we're going to square it, and then that's the probability of something happening. So the wave function will be a function of x or a function of time, and then you ask, well, what's the probability that the electron ended up there at that x with that time? And we get it from the wave function. Okay. How's that? Any questions at this point? So now, we're going to spend the next 3 weeks talking about these wave functions. 3 weeks or so. And I think it's worthwhile to go back, well, let's call this an introduction or a refresher, depending on whether you've seen it before, on waves. Okay, I think probably a lot of you have seen it, but I want us to all be on the same page about a wave. This is simple mathematics, although there's a fair amount to it. I mean, of course, we all know what a wave is. You go at the beach and you see a wave come in, that's a wave. Okay, but let's talk about waves mathematically. Let's just have a common language. Okay, so waves. So if I have a function of x in time, and as I mentioned earlier, whenever something is new and deep and complicated, we give it a Greek letter. By convention in quantum mechanics, we always call the wave function psi. Okay? But it's just a function, right? Just a mathematical function. But it's of x in time. It is a wave if it obeys a wave equation. You did a wave equation when you studied electricity and magnetism and you looked at light. Because light follows a wave equation. This is a wave equation. Okay? I mean, it's particular wave equation. It's for a free moving wave, but fine, that's the wave equation. Okay? And a common solution, there's many solutions. It's simply A times the sine of kx minus omega t. Right? How do I know that's the solution? Well, this is a little messy equation, right? I'm taking the derivative on one side with respect to x, and I'm taking the derivative on the other side with respect to t. Do you know what the name of this type of equation is? Here's some muttering. It's called the differential equation, just because it's derivatives. I'm not saying, well, and you've seen it before. F equals ma is a differential equation. A is two derivatives of x. But here I'm mixing up. I got derivatives of x and t. Also, I use this kind of curly d instead of that one. That means psi is a function of x and t, and here I'm taking the derivative only of the x with respect to x, and here only with respect to t. Those are called partial derivatives. I'm sure you've seen that. So this is a partial differential equation. And how do I solve a partial differential equation before I've taken my partial differential equations class? Okay, which is the situation, I think, for all of you. You guess at a solution. And if the solution works, there's a theorem you'll prove pretty soon in a partial differential equations class, which is if I find a solution, you can mathematically show that's the only solution. Okay? So if I guess and it works right and I guess right, then I'm done. There is no other solution. I've solved it. There may be, there's not a better solution. Sometimes there's multiple solutions, but there's not like you were wrong and there's a different one or a better one. Okay? There can be ones that also work, but are equivalent. So I'm going to guess that this works. And why am I going to guess that this works? If I take the derivative of this with respect to x twice, taking it once, sine will turn into cosine, and again, cosine will turn into sine. The same with the dt. And at this point, v is just a constant. I mean, as most of you probably know, that's going to be the velocity. But let's pretend I didn't know that yet. Okay? So let's just try v squared, two derivatives of psi with respect to x If I take the derivative of sine, I'll get cosine. K is inside, it'll come out. That'll happen twice. I'm going to get a negative sign when I take the derivative of the cosine. And then I'm going to get sine kx minus omega t again. So that's the right side. And on the left, similarly, I'll get A. I have minus omega squared, minus omega twice, so it gets squared. I take the derivative of sine, I get cosine, the derivative of that gives me another negative sign. And then I'm back with the sine. Okay? And the minus ones are on both sides, A is on both sides. The sinusoid cancels out. And I have V squared equals omega squared over K squared. This minus sign squares away, which is just to say V equals omega over K. So at this point, we can just treat this purely mathematically. I guess that a sine or a cosine, if you plug in a cosine, I think it's clear, right? It'll work just as well. If I plug in a sine or a cosine, I made it a function of x and t, and I just chose these constants in front of x and t. I just chose them, right? I did stick in a negative sign, which I'll come back to. It has a meaning. But for now, we just say there are two constants. And all I've learned is that this indeed will solve the wave equation. And this is the relationship between the variables I've got. OK? Just mathematical at that point. But of course, this isn't just mathematical. I mean, there's more to it than that. First, let's look at in time. There's the notion of a period of a wave. OK? So if I have psi at some x and some time, you can ask the question, and the wave, well, sorry, let me back up. What do waves do? What does this thing do? It's a little bit, and this is all I really want to get across today. It's a little bit complicated, and you may not be that used to having, you know, a sign you're used to, but having x and t inside the argument, right? And in this combination, all right. And that's what we're going to explore. But of course, the first thing I can say is let's pick t equals 0. So this term is gone, and that's just, you know, sine of kx, right? It's just a sinusoid. Similarly, if I pick x equals 0. This is just sine of omega t, all right? But then if x and t both move, it gets more subtle, all right? So one thing I can ask is, for any old value of x, let's let time progress. And this argument you need to learn, so you're used to being able to do this. It's very simple. Let's let time progress, and I want the wave to come back to be the same value it was at some time t. Sometime t plus capital tau later. Capital T is called the period. And it's 1 over the frequency, right? So if I have a wave that's oscillating, I'm just asking, when does it come back on itself? And that's a mathematical statement that it comes back on itself. So then I'm asking that A sine kx minus omega t equals A sine kx minus omega little t minus omega capital T. Now for any old sine or cosine, the sine of some angle theta plus 2 pi is the sine of some angle theta, right? Basic trig fact, okay? So all of this equals all of that if omega times capital T is 2 pi. Where t is the period. The capital T is the period. And therefore, omega equals 2 pi over t. Right? Simple. So that was when I just chose to put a constant in front of t, that is the meaning of that constant. Okay? Oh, sorry. And there's one other thing I could say about that, which is also that t is 1 over the frequency. That's just definition. If I have something that has a period right, of 10 seconds, the frequency is 1 over 10 seconds, and that's called hertz. So if that's the case, then omega is 2 pi times f. Just plugging in 1 over t equals f. And this is sometimes where f is called the frequency, this is often called the angular frequency, okay? And it's more natural mathematically to use it because it makes you write 2 pi less often, okay? So we're going to use it all the time, but it's nothing more than the frequency multiplied by 2 pi. Similarly, and I won't write it out as fully this time, if I ask the question, when does a wave at one point in time in space x, when does it replicate itself at some other point x plus a wavelength? Since I multiplied x by k, I'm basically requiring k times the wavelength equals 2 pi. And therefore k is 2 pi over the wavelength. Right? This is straightforward, and if you've seen it, maybe you just think you got it under your belt, but it's worth thinking about it just a second, make sure you really understand that. If this is the solution to a wave, the meaning of a wavelength comes from that reasoning. When does the wave get back to the same value? It's like x advances to x plus a wavelength, and so the k times the wavelength has to be 2 pi, because then it'll have no effect. So k is 2 pi over wavelength. Similarly for period. All right? Now, that's all well and good, but what if x and time, position and time, change together? Okay? So you can have a wave which is just something versus x, and it's just a sine, like a sinusoid, sine or cosine. I draw it, and it sits there. Or I could say the same thing in time. This is the time axis, and I draw it, and it sits there. When I make that construction, though, it's moving in time and space. And so let me ask the question, suppose I'm at some point on this wave. Now imagine a real wave on the ocean, and I pick the crest. Psi has some value, the maximum value it has at that point on the crest. Let's ride the crest. Let's go to some time t plus dt later, okay? And let's go to some x plus dx. And I want to still be at the peak. All right? So that's simply to say that let's go back to my actual form, sine kx minus omega t equals a sine kx plus k dx plus k dx minus omega t minus omega dt. Here I don't want to talk about 2 pi. If I just simply have these two pieces cancel within the argument there, in other words, if k dx minus omega dt is 0, then this is the same as that. And I don't worry about whether I'm actually a whole wavelength away or not, because I didn't want an argument like that. I wanted it always to be true. And then this is simply dx dt, solving this, is omega over k. And I already said that omega over k was v, which of course is just dx dt. And so basically what I've proven was that when I write the wave equation this way, this constant, I could have taken it just to be a constant out front, is indeed the velocity. Okay? So that's the basic thing about a wave equation. Notice one last point. If I choose a wave written this way, kx minus omega t, is it moving, taking the x-axis going that way, is it moving towards positive x or is it moving towards negative x? Yeah.
Positive x?
Why?
Because think about phase shift in the sign equation with the negative of t has something to do with a positive phase shift.
It is about that. It's really pretty simple. Dx dt was v just from what I constructed here. Okay? And what did I say? I just said, look, go to a later time dt, and change dx, and what happens? And the answer is, well, if dx and dt are related this way, which is just the velocity, then this is the same. If, however, I choose a way, oh dear. Am I still alive? Yeah. That thing unscrews and then just falls off. If, however, I choose a wave this way, plus omega t, okay? And then I say, I say psi of x plus dx and t plus dt equals psi of x and t. Then I ask k dx plus omega dt to be 0. In other words, the two bits I added in, they have to sum to 0. And then that's to say dx dt is minus omega over k. All right? In other words, to think a tad mathematically, just looking right here, if there's a negative sign between these two terms, if t advances in a positive direction, x advances in a positive direction and cancels it. All right? So as time goes forward, x goes forward, but they cancel each other, which is the statement that how I derive the velocity. If I put them in both with the same sign, if I go to a slightly later time, I have to go to a slightly lower value of x. I have to go backwards in x. Okay? So it is just simply a positive sign is negative going wave, negative sign is positive going wave. Okay? Have you guys, I mean, for how many of you is this sort of new? For no one? Oh, okay. Really? A couple of you raise your hand. Okay. I assumed it was new for more of you, but that's great. So maybe I can speed up. I guarantee you if I ask in an exam, though, I put in a positive and a negative going wave, a lot of people will miss it. Okay, so just do pay attention. Okay. This is mathematical, but there's one amusing little aside that I'd like to make. In fact, I'll be kind of surprised if you guys have seen this, but maybe you have. In fact, any mathematical function, f, is a solution to the wave equation. It does not have to be a sinusoid. Take any function, exponent, x squared, or function, the thing squared, logarithm, yeah.
Does the first half mean frequency or function?
I'm sorry, that was a bad choice of f, wasn't it? That's what I did in my notes, I hadn't noticed. Let's call it g, a function g, not f, frequency, yeah? That's also a solution to the wave equation. To show it, I'm going to define phi, which is called the phase, which is the inside guts. I'm being I have to be a little bit formal here. I have to take the step of naming the interior. It's a function, I'll call it a new function, phi. Okay, my wave equation is v squared d squared g dx squared equals d squared g dt squared. Okay? Let's take this part. D, and I'll put a v squared there, d squared g dx squared. Okay, I have to go carefully. This is v squared partial with respect to x of dg dx. Okay? Equals v squared partial with respect to x. dg dx, well, basically when I do that, I'm saying g equals g of phi, which is let me just erase that word there. If I say that about phi, then I'm saying g equals g of phi of x and t. I mean, it seems like I'm just playing a little bit of a game, but I need that to evaluate this derivative. So then, by the chain rule, dg dx is dg d phi dx. D phi dx is k. Okay? So this is v squared k d by dx of dg d phi. Now taking d by dx of dg d phi is, once again, it's v squared d squared g d phi squared d phi dx. In other words, if if this thing is a function of phi, which is a function of x, then to take the derivative with respect to x is to take the derivative with respect to phi, and then the partial of phi with respect to x. And there was a k there. And so then this is v squared k squared times g. All right? Times the two derivatives of g. But similarly, if I look at d squared g dt squared, I play the same game. That's d by dt of dg d phi dt, which is d by dt. d phi dt is minus omega dg d phi. And if I do it again, I take that derivative through, I get to here. All right? And having said that v squared dg d squared g dx squared is just k squared times two derivatives of g with respect to phi, that will also, having said that and having said this, I am indeed solving the wave equation. Yeah?
Should it be dg or dt or dg
Ah! Sorry, phi. I'm sorry, phi. This was a bit mathematical, but the point is, there's this wave equation, and I think the solutions ought to be sinusoids or cosines and cosines, because you take derivatives of them and you get back where you started, or take two derivatives and I get back where I started. In fact, the solutions don't depend on that. I can have some ugly old function g, which when I take the derivative, I don't get back the same thing. Not at all. I mean, literally, I could have put in logarithm, I could have put in exponential, I could have put in, second order Bessel function, all sorts of stuff you'll learn about later, all right? When I construct it with kx minus omega t as the argument, the wave equation still holds. I just get this ugliness on both sides, the second derivative of g with respect to the argument, okay? And so that's why you can actually have, you can actually construct a solution, and this is important even for quantum mechanics. I can have a solution to a wave equation which is maybe a hump that looks like that. That is not a sine, that is not a cosine, okay? This would be something of x, or I can do it of t. But if I construct this thing in such a way that the argument inside, instead of like one thing, like I might have plotted this as g of y, but then I say y equals kx minus omega t, where y is just some arbitrary variable. It will obey a wave equation, it will move to the right. Okay, just like a wave. So a wave can be just like a pulse, or any old shape. If it's got if the argument inside is kx minus omega t, it will move. Okay? And a lot of particles we want to deal with in quantum mechanics are going to be more like that than this other thing. Okay. That being said, this is something that mathematically gets more complex, and we're not going to deal with very much. We'll deal with some. So we're mostly going to stick with sines and cosines. However, sines and cosines have one slightly annoying feature, which is if I take the derivative of a cosine, I get a negative sine. And if I take the derivative of a sine, I get a cosine. So instead of those, another way to write the solution to the wave equation is a e to the I kx minus omega t. Okay? And again, the wave equation is d squared psi dx squared equals d squared psi dt squared. And so d squared psi dx squared is what? I just take two derivatives of this. A goes along for the ride. When I take derivative with respect to kx, I get k and I twice. So this is k squared times psi and a minus sign, right? Because of course I here is the imaginary number, the square root of minus 1. And d squared psi dt squared is similarly minus I omega, all of that squared times psi, which is the minus side gets squared away. I squared is minus 1, so it's minus omega squared psi. And so this will solve the wave equation because I have k squared, I have omega squared, and both of them have a negative sign. And so then if you plug in, of course, they just solve the wave equation. So this is a little more convenient, though, because if I take one derivative of this with either time or space, I get back the function again with some constant out front. The annoying factor there is now I've got a complex number. I've got a complex function, e to the I kx minus omega t. Actually, that is still, mathematically, even though it's complex, it's a lot easier to deal with that. And so you're going to be dealing with that, a lot as you go on in physics. And, we shouldn't be afraid of it. Of course, it's just coming from Euler's theorem, right? E to the I phi equals cosine phi plus I sine phi, right? You heard the story about Euler? The story about Euler. Euler was, I remember when I was in high school and I first saw that equation, I just thought, what in the world does that mean? And how did anyone ever figure it out? Okay? You can actually, comes from Taylor series and a definition of cosine and sine in a more rigorous way. And if you haven't seen it, there's a way you get this. It's not all that whacked out. When I saw that, I thought that just, this guy's from outer space. But anyway, I heard a story about Euler. When he was young, and he was in school, the class was acting up, it was math class. And the teacher got mad and said, all right, here's punishment. Numbers 1 through 500, add them. And so everyone sat down with their piece of paper and they literally had 1 plus 2 plus 3. And they're just sitting there starting to add 1 through like 500. And Euler sat there for about 30 seconds or so. And then he starts goofing around again. And I think it's like, 18th, 19th, 17th century, right? Hardcore instructor, he's, all upset. And Euler says, well, I've got the answer. And what he'd realized is you're going to add 1 plus 2 plus 3 plus 497 plus 498 plus 499 plus 500. 1 plus 500 is 501, and 2 plus 499 is 501, and 3 plus 498 is 501. I just got to figure out how many 501s there are. And I just, if this is an even number or if it's an odd number, you get a slightly different formula, and you can write the answer down. And he did. I think he still probably, back then got swatted. But anyway, so this is Euler's theorem, right? And So all we're doing is we're just saying this is a cosine wave where if I put, instead of phi, I put kx minus omega t, and that's a sine wave. So when I write things this way, I'm just mixing up a sine wave and a cosine wave. All right? And in fact, what in practice we do, this is a complex number though, right? It's a complex number, and you don't like complex answers to problems, especially if you write down a real physical problem and there's nothing imaginary in it. There's no I in it. What you do is you say, well, I'll say that this is the solution, but when I'm finished, I'll take the real part. And so you work some stuff out, and at the end, maybe you've changed psi into some other thing that's also complex. And you say, I started with the real part, then I'll just take the real part in the end, which is basically to take the cosine part. But then none of your derivatives are changing sines to cosines, and so all the math gets a lot easier. Okay? So in physics, we're always, and in mathematics, we're always dealing with that notation for a wave. Okay? Should I do a quick 1 minute on complex numbers? Yes? No? Yeah. All right. Well, kind of following from here, right? What's a complex number? Well, there's a couple ways to look at it. That's one way. There's just the idea, let's call a complex number, let's say it's R, which is A plus IB. Okay? So it's some real number plus some imaginary part plus some, A and B are real, so it's a real part, and then plus this imaginary term times B. And of course, you know, I isn't a real thing, but you can construct an algebra having stated it this way, and you can just follow the logical steps of the algebra, and all sorts of wonderful and interesting things happen. And that's the usefulness of complex numbers, even though what in the world I really means, you don't know. In fact, you just say, look, I is just a thing. Basically, you know, instead of getting all upset about what in the world is the meaning of the square root of -1, it's really different. What you're really saying is, we're just going to invent new rules for multiplication such that some of the numbers, when I multiply them by themselves, I get a negative sign in front. I'm just kind of redefining multiplication in a certain way. And I'm just building up a new algebra and examining the consequences. Okay? If it keeps you awake at night worrying about square root of -1, that's a better way to look at it. Okay? So then, of course, there's the notion of a complex conjugate, which is just every time I saw an I put a -1. And then, if I do R star times R, that's called R star, or the complex conjugate of R, this is just A minus IB times A plus IB, which cross terms disappear. This is just A squared minus IB squared, right? Just simple algebra. And I squared is -1, cancels that's -1, so that's just A squared plus B squared. Okay? So what we'll say then is that the magnitude of the complex number R is just that. And the symbol for it is to draw two bars. Okay? Now, let's relate this to here. I won't prove Euler's theorem. All sorts of questions arise when I'm working with complex numbers. Like suppose I have to divide two complex numbers. I can do it. It's often easier to use it in this form. I want you to be able to do one thing. You're not going to have to use complex numbers a lot, but you're going to have to use a little. I want you to be able to do one thing. I want you to be able to move between this form of a complex number and that form. Okay? How do I do that? I'm not sure you guys have seen this. If R equals A plus IB, okay, I'm just going to play a little bit of an algebra game. I'm going to multiply this thing by A squared plus B squared. In other words, the length of R, often called the norm of R. I'll multiply and divide that on each piece. Okay? And note that this term is a number which is strictly less than 1. You can think of this like a triangle with lengths A, B, and A squared plus B squared is the hypotenuse, and an angle phi there. Okay? And then this is, if that were just a triangle, that in fact is the cosine of the triangle. Just, I mean, stare at it a second, it is. A is this side, and that's the hypotenuse. So this simply can be written as the square root of a squared plus b squared times the cosine of an angle, phi, plus I times the sine of an angle, phi. Because b is also exactly the sine of that triangle. Okay? And so, in general, I would say that I can represent the complex number that way. Well, equals the magnitude of r, which is equal to r star times r, which is equal to the square root of a squared plus b squared. And phi, just from this triangle, the easiest way to talk about phi is that the tangent is b over a. So phi is the inverse tangent of b over a. Okay? So you may or may not have been familiar with that. You need to have that under your belt. Just move back and forth. Okay. Good. I'm done with just talking about math. And let's get back to quantum mechanics. So, that was kind of a detour, just to look at waves and dealing with waves. And let's remind ourselves, so we had P was h over lambda. This is what de Broglie said. Which is, I'll divide by 2 pi, and I'll multiply by 2 pi. And 2 pi over lambda, remember I derived it a while ago, this is the k number. That's just k. K was 2 pi over lambda in a wave. H over 2 pi, this appears so often that we define a new constant. Well, having last week for the first time introduced you to the Planck's number h, it turns out Planck used the wrong number in terms of a convenient constant. The convenient constant is to divide h by 2 pi. That's much more commonly used, h bar. There's a coffee bar in the basement in the ground floor of the Seattle physics department called the h bar. Nice geeky thing. Remember also that we had this result from the photoelectric effect that Einstein introduced, right? This is how we started in this whole quantum mechanics mess. Once again, if I divide this by 2 pi, then I get to multiply the frequency by 2 pi, and then that was the angular frequency. So I sort of have these two results, okay? But now k and omega, they have this interpretations in terms of a wave. K is modulo the factor of 2 pi is the inverse wavelength, and omega is the frequency, modulo a factor of 2 pi. Okay. What do I want to do next? Well, we can't just derive this from F equals ma. We're taking a leap here to quantum mechanics. So I simply have to postulate some things, and it turns out this seems to work. And so the basis of quantum mechanics is a little ad hoc, but here's how it goes. If I have psi, as we've talked about, I notice that if I take d psi dx, I'm going to get, I have to change colors here. No, that's white. if I take the x derivative of psi, I'm just going to get ik times psi. So instead, let's do h bar over I times d psi dx. And then that's just going to be, I'll divide the I out and I get an h bar, so that's h bar k times psi, which is p times psi. Just sort of notice that as a mathematical thing. And then what we do, here's the thing. We say, okay, the momentum is h bar over I d by dx. Somehow, momentum, which used to be m times v in quantum mechanics, is the constant h bar divided by I, the imaginary number, times the partial with respect to x. Okay? That's what momentum now, how it shall be represented. It still was going to have the meaning we're used to. But mathematically, it's now its basis. It is not 1/2 mv squared. In fact, velocity disappears in any simple way from the discussion of quantum mechanics. Instead of velocity, we talk about momentum. And instead of writing mv down, you write this down. Okay, and I'm going to come back in a second to what that might mean. In fact, I'll probably get to it at the beginning of next class. So that's A. I need one more step, and then I can leave you with a good thing for the end of the day. So notice also that d psi dt is minus I omega psi. And so if I multiply this by I h bar, this will be h bar omega, and the i's will cancel psi. And so therefore we say I, the energy, is I h bar d by dt in some way. Then let's just write down the simple kinetic energy of a particle. Instead of 1/2 mv squared, it's p squared over 2m. Right? If p is mv, that is 1/2 mv squared. And let's say that this is the definition of I and p. And let's say that I want to multiply these things times psi. In fact, then I'm going to reverse the order here. Sorry, I want to reverse it. Erasers work better on the chalkboard than your notes, so I'm sorry for that. But this is just convention. And so this is taking p, h bar over I d by dx squared, and you guys probably know this is Schrodinger's equation. All right? So in quantum mechanics, I've got 30 seconds to talk about this. In quantum mechanics, the basic equation is nothing more than the energy of something. If there's a potential energy, if there's a force, then we always talk about the potential. We don't talk about the force directly. We would never, with the mass on a spring, try to somehow talk about F equals kx. We would write down that the potential is 1/2 kx squared. So if the energy is p squared over 2m plus v, we then just generalize this by sticking in a term which is just right here, which is v times psi equals I h bar d psi dt. And that's the more general form of the Schrodinger equation. And so what this is kind of ad hoc, right? Made up. I knew that somehow I had to associate a momentum with the particle. I had this notion from de Broglie that it ought to be inverse to the wavelength. And we also have, from the way photons behave, that the energy ought to somehow depend on the oscillation, the frequency. And so I just make these two associations and I stick it into an energy equation. And that's a derivation, if you will, of the Schrodinger equation. There are other ways to get the Schrodinger equation. They're just as much sort of just brought out of thin air as that, because there's no foundation. You can't go from F equals ma to this. But this has been well proven over and over again. And so this is the foundation of quantum mechanics. We're going to then learn how to solve this equation and find psi. Psi represents the probability, and then we'll start going on. Okay? So we'll stop there.